recording now. So here we are. We're at the end. Believe it or not, you made it. And we're going to be finishing our review for the final exam. I'm going to pick up where I left off. And just in case anybody's joining us who wasn't here last time, I'm going to begin by sharing my browser with you and showing you where I'm getting the information from. Okay, here's our course, and we're currently in week 16 of the course. And what I'm going over today is this final exam practice file. Okay, this just has questions in it. It has an answer key, but it doesn't show you how the problems are worked out. So what I'm going to do is actually show you step by step how these problems are solved. Okay, so that's what I'm using. Before we leave the course here, let me just point out a few things. Okay, this week, the only assignment you have besides studying for the final, of course, is grade check 4. Okay, this is a last opportunity for you and I to talk about grades. Again, if you have additional questions or concerns, I would encourage you to please send me an email, reach out, and we can discuss whatever your concern is. Here is an extra credit opportunity. Please do not spend time on this in lieu of studying for the final. Okay, what this is a link to another Canvas course that deals with math in different cultures. And it's not what you would think of as school math. It's mathematical thinking, how people use mathematical thinking to solve everyday problems in their culture. Okay, here is next week. Here we have our final exam and the final exam work. This is where you would upload your work so I can give you partial credit on the final. Our final is due by Monday at 11:59 p.m. Please, please, please don't miss the final exam. Okay, if you made it this far, don't miss the final exam. Again, if you have any concerns about the timing of it or whatever, you think you're going to have an issue, please reach out and let me know, preferably in advance. Okay, there isn't a lot of time to make up things now. We're kind of at the end of the semester, and there's a requirement that I have my grades in by next Friday. So again, please reach out if you're having any difficulty at all with anything. Okay. All righty. So what I am going to do now, if you would give me a moment, is I am going to share my tablet with you, and that usually takes a while. So again, please be patient. Okay, again, I'm going to be picking up on the final exam practice with question 18 because we left off with 17 the last time. If you're looking for the solutions to those, please check either the video recording that's in our week 16 online sessions, or there's also a solution key there. If you don't want to sit through the entire video, you can actually see the worked out solutions. Okay, so let me share this content with you now. Okay, and everybody should be able to see my notes that show the review problems. Okay, so again, if you've got any difficulty with technology, you're not seeing what I think I'm showing or anything like that, please just unmute yourself and ask a question. Right, so I'm starting with question 18. And again, there were a set of a set of directions here, and they wanted us to find intervals of increase, decrease, maxima and minima. Okay, and so pretty much 17 and 18 are similar problems. The only difference is the functions that they're giving us. Okay, 17 was a polynomial. Okay, so it was a relatively well-behaved function. This function is a rational function. Okay, and again, we can rewrite this function with a negative exponent. So I can write this as 1 minus x squared to the minus 1. Okay, again, rewriting it that way makes it easier for me to do calculus on it. I'm going to need to do calculus in order to find intervals of increase and decrease. Okay, yes, you can check graphically, but I'm kind of expecting that you're going to use some calculus. But again, it's an online test. If you can get the right answer, however you get it, it's fine, as long as you're not asking your friend or your brother or somebody else. Okay, so basically, in order to find the answer to this, I'm going to need to find the first derivative, right? Set it equal to 0, okay? And then determine where it's undefined as well as where it's increasing or decreasing by doing an interval test. Remember, the sign of your first derivative tells you what it's doing in an interval. And those intervals are going to be separated by critical numbers. What are critical numbers? They're places where the derivative is either undefined, okay, or where the derivative is 0. Okay, so you've got to test in each one of those intervals. Okay, so again, I'm going to start by doing f prime of x. Okay, again, I need to use the chain rule on this because it's a polynomial inside of something else. Okay, so first I'll bring down the exponent, leave what's inside alone, drop the exponent by 1, that's the outer function. And then I have to differentiate the inner function. That would be negative 2x. Okay, so there's the chain rule. I kind of want it in an easier format to work with. Okay, I mean, I can leave it like that, but I'm going to rewrite it again using a little bit of algebra. Okay, you see we have a negative sign out here times another negative over here. Okay, so these two negatives give me a positive 2x. That's in the numerator. The negative 2 on this parentheses puts it in the denominator with a positive exponent. Okay, so that would be a simplified version of this derivative. Okay, the first question I'm going to ask is, where is this derivative undefined? Because it does have a quantity with x in the denominator. And again, those undefined spots give me critical numbers. I think you can see that as long as this x squared would equal 1, okay, this entire derivative would be 1 minus 1 squared, which is 0 squared, which is still a 0. Okay, and that's a problem. So what I'm going to put over here is a note that says undefined if x equals, now because I'm squaring x, I have a problem if x is 1, of course, but I also have a problem if x is negative 1, because if I square a negative 1, I get a positive 1, and 1 minus 1 is 0. Okay, so everybody's good with that? All right, I also have to figure out where the derivative is 0. Okay, so I need to set this to 0. Okay, and again, what I want to kind of explain to you is if you set this thing to 0, okay, you know what's going to happen when you try to solve for x is you're first going to multiply both sides by the denominator to get rid of it. Okay, so you'll have no denominator on this side because you would have multiplied this side by the denominator. And then when you multiply this side by the denominator, it's going to become a 0 because you've got a 0 over there. So you're going to wind up with 0 equals 2x. You may remember from college algebra that whenever you have a rational function, any zeros, any x-intercepts, okay, happen basically when you've got, you come from your numerator, okay? So I'm setting this equal to 0, okay, and I'm trying to figure out what x values give me that, okay? And you can see if 2x is 0, then x has to be 0 as well. Okay, so I've gotten 3 critical numbers here. Why is it negative 2? Are you talking about the derivative up here, Ethan? Is that what you're asking about? Okay, basically it's negative 2 because the coefficient on your x term inside here is negative. So when you take the derivative of this inside function, the 1 doesn't give you anything, okay? But the negative x squared gives you negative 2x. Okay, is that what you meant, or did you mean the exponent up here? Okay, you can type another question. The exponent, okay. Okay, it's 1 over 1 minus x squared. So I rewrote that as 1 minus x squared to the minus 1. All right, everybody good with that? A quantity in the denominator can be thought of as raised to the negative 1 power. Right? And then I'm using the chain rule to take the derivative, which says bring down the exponent, leave this thing inside alone, and drop the exponent by 1. So negative 1 minus 1 gave me the negative 2 as the exponent. That's the derivative of the outer function. Okay, and because it's a composition, then I have to multiply that by the derivative of the inner function, and that's where the negative 2x comes from. Okay. Anybody other questions? Okay, please don't hesitate to stop if you've got a question. This is for your benefit. Okay, it's not just so I can hold class. Okay, I really want to know if you're confused about anything. Okay. Okay, so is everybody all right with the 3 critical numbers that came out of this? I got -1, 0, and +1. Okay, and so the difference between this and number 17 was this derivative had places where it was undefined, and I need to consider those. Okay, so the next part of the strategy is to divide the number line with the critical numbers into intervals. Okay, so there's the critical numbers on my number line. Okay, and then I have to basically test the sign of the derivative in each interval. Oops. Okay, so what you do is you pick test number. Okay, and remember, you don't need to get an answer. You're just checking signs. Okay, so I'm looking at this 2 over 2x times 1 minus x squared squared. That's the quantity I'm checking. Okay, so suppose I put in a value like -2. Okay, you just have to check the signs. Okay, here I'm going to wind up with a negative numerator, right? Because 2 times -2 is negative. And then I have 1 minus 2. Remember, actually 1 minus 4. Okay, because remember, you're squaring this. Okay, so this becomes positive. Okay, my denominator is negative inside, but I'm going to square it. So the denominator looks like it will always be a positive number. Okay, so the numerator is what's controlling the sign of this derivative. Okay, does everybody kind of see that? Okay, so it's just a matter, even if this whole subtraction becomes negative because you're squaring it, it's not going to matter. You're always going to get a positive answer down there. Okay, all right, so that tells me in this interval where -2 is, the derivative's negative. Okay, I'm going to just kind of repurpose my fraction a little. All right, and I'm going to put in a value between 1 and 0, so -0.5. Okay, and again, you can see I have a negative numerator. My denominator, no matter what I plug into it, is going to be positive because of the square. So this is also negative. Okay, now let's change to between 0 and 1. So I might put in a positive 0.5 and a positive 0.5. Denominator is always positive. Now the numerator is 2. And the last one I would check would be the interval between 1 and infinity. Okay, so put in a positive 2. And again, they're both positive. Okay, so that's using the first derivative to test the sign in each interval. You can certainly do that with a calculator. Okay, but if you're writing down work, okay, you want to at least write down this number line with the signs of the derivative in each of the intervals. Okay, so I know that you checked. Okay, you don't have to write out all of this stuff. You can use a calculator for that. So basically what you want to say is this function is, this function is increasing on the interval from 0 to infinity. Okay, even though it's these two, you don't have to write them as separate intervals because it's increasing on the entire interval from 0 on out and decreasing from negative infinity to 0. Okay, is everybody all right with that? Anybody questions about it? Okay. Now we said that the function was undefined at 1 and -1, so we're not expecting any maxima or minima there because the function doesn't even have a value there. Okay, that means our only candidate for a max or a min is where the derivative was equal to 0, which is at the origin, is that at x equals 0. Okay, and it's not at the origin actually. Let's plug it in over here. Okay, if you look at this number line, you can see I'm decreasing down to where x is 0, and I'm increasing up from it. Everybody see that? Okay, decreasing down to 0, increasing up from it. That means x equals 0 gives us a local min. Okay, and they probably want the y value. So you would basically plug that in your function. Use the original function. Okay, so a local min is at 0, 1. Okay, how do we know if it's increase or decreasing? We're using the sign of the first derivative. That's what I'm doing here in part A. I'm checking the sign of the first derivative on each of the intervals, okay, that I created by putting in critical numbers. Okay, first I use the derivative to find critical numbers. That's where it's either undefined or where it equals 0. So I got these critical numbers, -1, 0, and 1. And then I'm checking in each interval, picking a number in each interval and plugging it in the first derivative. If the sign's positive, the function's increasing. If the sign's negative, the function's decreasing. Okay, so that's how I got these pluses and minuses on the number line up here. The other thing, again, that this tells you is the function is decreasing down to a minimum and increasing away from it, right? So decreasing to the left, increasing to the right means you've got a minimum right here. And that minimum 0, 1. Okay, so I know that without even looking at a graph. Okay, that's what the calculus is telling you. Okay, any questions on A and B? Questions on A or B? Okay, so the next piece is concavity. And you remember concavity and inflection points are given by the second derivative. Derivative. Okay, where the second derivative is 0 is likely an inflection point. Okay, and second derivative, I showed you this little mnemonic. If the second derivative is positive, 2 positive signs, concave up. Second derivative negative, concave down. Okay, so that's kind of a little mnemonic to help you remember what the second derivative tells you about concavity. Okay, now again, I'm seeing just a minimum here, so I'm expecting this function to kind of be concave up everywhere. Okay, basically because there's a minimum and nothing else. Okay, but let's see what we get. Okay, so the first thing I have to do is find the second derivative. I'm just going to rewrite the first derivative here. And I'm going to rewrite it in a form that I can actually use it. Okay, so I have 2x, that was in the numerator. Okay, and then I had 1 minus x squared to the minus 2. Okay, so I'm just deconstructing this fraction. Again, you've got to be really comfortable going between a fraction with something in the denominator and writing that with a negative exponent, because you're doing that constantly when you're doing calculus on things. Okay, so that's not calculus, that's just algebra. Okay, now you notice here I have a, I guess you would call it a product. Okay, so I kind of need to use the product rule. Okay, so I can say over here, I can say let u equal to x, u prime equals 2, v equals 1 minus x squared to the minus 2. And again, I'm going to have to use chain rule. Okay, so basically, let me just take a moment. Okay, so basically, what I'm going to try to do here is do the chain rule. Okay, so b prime is bring down the 2, 1 minus x squared to the minus 3. I'm dropping it yet again. Okay, and then I need to multiply that by the derivative of the inside, which is what? It's minus 2x. Okay. All righty, so now I have to use the product rule formula. I'm just going to put the pattern for it here, u times v prime plus v times u prime. And I'm just going to copy my pieces. So I have 2x times, I'm going to multiply here, minus 2 times minus 2 is positive 4. Okay, so 4x times 1 minus x squared to the minus 3. Okay, so that's u times v prime, and all I did was multiply these two together. Okay, everybody good with that? Plus v times u prime. Okay. And then the rest is like a bunch of algebra. Okay. So basically, if I want to collect terms out here, you can see I have a 2x and a 4x. That gives me an 8x squared. This quantity is in the denominator. Okay, so that's the first term. And then this term is a 2 times, this is a minus, 2 over. Okay, so there's my second derivative. Okay, this second derivative was messy because I had to use the product rule. Okay. Could have also done this with a quotient rule. If you had just left it in the denominator, you would have wound up with a variation of the same thing. Okay. The main thing I want to point out here is I've got the same issue. Okay. If I try to solve this for, if I try to solve this for 0, okay, here's what happens, okay? Basically what I have to do here, if I want to try to solve it for 0, I can do this, okay, set it equal to 0. I'm trying to locate inflection points. Then I'm going to get, if I move one term over to the other side, it becomes negative. Okay, so I just moved the 8x squared term to the left, so it became negative. And now I can treat it like a proportion, and I can cross multiply. Okay, now what you should realize is these are a common factor, right? So I can divide out one of them. Okay, I can get rid of one of those. Actually, I can get rid of 2 of them. Okay, so this goes away. And I'm left with just one of these. Okay. And then the rest is just algebra. Okay, it's quadratic. So basically, it's a quadratic with just a square term. So what I can do is I can try doing this. I don't need to use like the quadratic formula or anything because I just have a single square term. I can use the square root property. Okay, divide both sides by -6. And here's where you stop. You've got -1/3 equals x squared. Okay, and you should remember you can't take the square root of a negative number and still be in the real number systems. So this has no real solution. What does that mean? That means no inflection point. Okay, that's a long way to go, right? What I would recommend is this is the calculus algebra solution. Okay, it's not always easy to see an inflection point on a graph. Okay, you may need to expand the graph a lot, like in Desmos, to make sure it doesn't change concavity. Okay, but I'm kind of guessing that this graph, remember I said I kind of think it's going to be concave up everywhere. Okay, so basically, how would I tell that? Well, you'd have to check the sign of the second derivative, okay, and see what kind of concavity we get, okay? So basically, if you plug in each of these intervals in here, okay, you get kind of a set of, at least here around your 0, it's going to be concave up. So again, I'm just doing the same thing. I'm plugging in test points, okay? This denominator will always be positive. This one won't, okay? Because it's got a cube, right? So again, I'm running out of room here, okay? And I don't want to take, a ton of time on this problem, but let me just explain. You would pick a point in here, plug it in here, and figure out what's the sign on this term, what's the sign on that term. And again, basically, what's the sign on the answer, okay? You can also just plug in values in your calculator and actually figure out what's the value of this and decide whether or not it's positive or negative. I'd recommend a calculator approach here, okay? So again, my attitude here is if you want to check on the graph, this is going to be a rational function. So it's going to be very easy to see the concavity, all right? So since this is getting super complicated as far as where it's concave wherever, okay? Let's take a look at the graph. And again, you can see no inflection points. That's important. but let's look at the concavity on a graph. Okay, so I'm going to graph the original function. I'm going over to Desmos. Okay, and we'll graph the original function over here. Okay, so that's y equals 1 divided by, and again, that would be 1. I'm going to put it in parentheses, 1 minus x squared. Whoops, arrow out of that, squared. Okay, so here's what our original function looks like. Make sure you look at what Desmos is rendering. Okay, so you're sure it's seeing what you're trying to type in. Okay, so let's look at concavity. Here is this middle part of this rational function. It's easy to see this is concave up, and it's easy to see we've got some asymptotes, right? Remember, we said this function was undefined when x equals 1 or negative 1. I don't know if Desmos will let me graph vertical lines. It does. So there are the two asymptotes. Okay, it has vertical asymptotes at the undefined spots. All right, here's our minimum. You can see that. Then we also know this function is concave up, okay, from negative 1 to positive 1. You can see it right here. It's never going to reach negative 1 or positive 1 because it's approaching asymptotes. Likewise, you can see the concavity very clearly here. It's concave down. And it's concave down on this side as well. Okay, so the concavity of this function is concave up between negative 1 and 1, and concave down between negative infinity and negative 1, as well as between 1 and positive infinity. Okay, so what I'm asking you is everyone see the concavity. All right, see the concavity? Everybody see it? So what I'm telling you to do is switch tools, okay? The calculus algebra road is becoming complicated. So that's when you take a look at the graph, okay? And if you actually do need a calculus algebra solution, it should match what the graph told you, all right? Since you're taking an online exam, okay, basically it would be enough to say, I got the graph, here's what the graph looks like, and I'm determining concavity from the graph. Okay, if you're showing me work for this problem, realize the online exam doesn't care how you got the answer. It just cares whether it's right or not. Okay, but if you're showing me work, it's perfectly acceptable to say, I looked at the graph and I determined the concavity from the graph. Okay, again, assuming you're correct. Anybody questions about this one? Don't be afraid to switch to a simpler solution if what you're doing is getting bogged down. Okay, if you've got a simpler solution, use it. Okay, so here's what we found. Concave up, the intervals from negative 1 to 1. Concave down, we've got 2 intervals from negative infinity to negative 1, or from 1 to positive infinity. Those are the 2 elbows on the graph. Okay, anybody problems with it? The asymptotes were the undefined spots. Okay, we found those early on. Okay, they're vertical asymptotes. Okay, the graph also has a horizontal asymptote. Okay, these are vertical asymptotes. Now, again, you might remember from college algebra, if the denominator of your function is larger than the numerator, the degree of it is. Here I've got a squared in the bottom and a 0 power on x up here. Okay, this approaches the x-axis as an asymptote. Okay, so this would be y equals 0. And again, if we go back to the graph, you should be able to see that. Okay, see the asymptote? Okay, so again, okay, everybody make sure you can wangle the graph to tell you what you want. Okay? Everybody all right with this? Again, I'm pretty sure the horizontal asymptote is pretty obvious. Okay. Now, again, this is a heavy algebra question. Okay, again, there may be one like this on the exam. There may not be. And again, what I'm telling you to do is leverage the tools you have at your disposal. You're allowed to use any tools I put in the course. You're allowed to use online tools. If you have a TI-84 and you like it, you're allowed to use that. The only thing you're not allowed to use on the exam as a resource is somebody else. Okay, your friend, your brother, a tutor, okay? It has to be your work, but you're allowed to leverage anything at all. Okay, so I'm going to stop here and ask, are we okay with number 18? All right. Okay with number 18? All right. Again, I'm not seeing questions. I'm assuming if you have them, you'll ask them. Okay, I'll try to pause briefly. There is a space on this problem to sketch the curve. And again, you would just attempt to copy the notable features of the curve, which of course are the vertical asymptotes, the horizontal asymptotes. Okay, so this doesn't have to be a work of art. It just has to show the features of the graph. Okay, good. All right. Now, the rest of this review deals with integration as well as applied problems. The first part are basic integration problems. That's kind of like 19 through 25. And the remainder of them are sort of applied problems. Okay, I definitely want to try to go over everything, but I want to make sure you see the applied problems. So if we start bogging down in the general integral problems, I reserve the right to skip the rest of those so I can show you the applied problems. Okay, so here's a basic definite integral. Okay, you take a look at it first. Whenever you're doing a definite integral, take a look at the function. Make sure it's going to be defined on the interval that you're integrating over. This is a polynomial. It's defined everywhere, no problems. Okay, so I'm just going to use the power rule on it. And again, I'm going to find the antiderivative first. Okay, so basically doing that is just repeated applications of the power rule. Pull away the coefficient, add 1 to the exponent, write it over the new exponent. Okay, do the same thing with the next term. Pull away the coefficient, add 1 to the exponent, write it over the new exponent. Okay, don't do the algebra while you're doing the calculus. Do the algebra next. This needs to be evaluated between 1 and 2, but first I'm going to do the algebra. Okay, 4 goes into 8 twice, and the 3's cancel. Okay, and that's a lot simpler to evaluate. And then you're going to use the fundamental theorem to evaluate it at its upper bound. So I'm going to plug in the 2. And then you're going to evaluate it, subtracting it, evaluate it at the lower bound. Again, this is a calculator problem. Okay, don't do this stuff in your head. Okay, use a calculator. And when I did, I got 37. Okay. Again, I'm just trying to show you the basic outlines for these. I took a look at the homework. Most of you did all the homework, which is great. So you understand how to do these. Okay. If anybody has a question, just bring it up. Okay. If I don't manage to answer your question right now, hold on to it until the end of our class, and I will take time at the end of class to answer any specific questions you might have. Okay. Since this is the last time we're going to meet before the final. Okay. Unless you schedule a separate meeting. Okay. So if I can't answer it now, or I ask you, please hold on to your question till the end, ask me at the end. Okay. Here's the next one. Okay, if we take a look at this, it looks kind of complicated, but the first thing you want to decide is, would I be able to integrate this, okay, using the fundamental theorem? Well, the only value that would make this undefined would be if u were 0, and 0 is not in this integration interval. So I think I'll be able to do the integration. Okay, you've always got to check. Does the fundamental theorem apply? Because remember, if your function's undefined anywhere in there, you're not going to be able to use the fundamental theorem. Okay, it's not valid. Okay, think of it this way, and I said this on exam 4 over and over again. Think of it this way: this thing has an asymptote or something that's undefined at 0. Okay, and what might happen is if it's a vertical asymptote, for example, your area under the curve may shoot off to infinity there. Okay, so you don't want to be trying to find an infinite area or anything like that. Now, I want to simplify this before I get started. So here's the way I'm going to rewrite it. This is just algebra, not doing calculus. Okay, so what am I doing here? I'm taking the denominator, which was a common denominator, and I'm writing each term in the numerator over it. Why am I doing that? Because then I can use properties of exponents to simplify things. Like this. Okay, this is u to the 1/2 divided by u to the first. This is 2u squared divided by u to the first. Okay, and you might remember the quotient rule for exponents. If you're dividing two powers that have the same base, you subtract the exponent in the denominator from the one in the numerator. Okay, so before we're doing any calculus, okay, this winds up giving me u to the minus 1/2, and I got that by subtracting 1 from 1/2, which gives me negative 1/2. Okay, here I'm subtracting 1 from 2. That's just going to give me a u to the first. So here's my simplified integral. Okay, so I needed to do all of this algebra just to get it in the form that I can actually integrate. Okay, so again, what rules did I use? Well, this is a basic rule of arithmetic. If things are written over a common denominator, you can write each term in the numerator over the common denominator. Okay, you usually use the rule in reverse when you're simplifying fractions, when you're adding or subtracting, but it works in both directions. The second rule I used was I wrote my square root as a fractional exponent. And then the third rule I used was the quotient rule for exponents. Okay, that says if you're dividing powers with the same base, subtract the exponents. Okay, so that's the extent of the algebra. Now I can finally do some calculus. Okay, and I'm just going to use the power rule over and over again. So this is going to be add 1 to the exponent. So adding 1 to negative 1/2 brings this up to positive 1/2. Write it over the new exponent. Pull away the coefficient, add 1 to the exponent, write it over the new exponent. Okay, so that's the calculus bit. Okay, this is going to be evaluated between 1 and 9, but I'm going to simplify it first, of course. Okay, here, dividing by 1/2 is the same as multiplying by 2. And I can rewrite u to the 1/2 power as the square root of u. In the second term, the u's cancel, and I wind up with u squared. Okay, that looks a lot easier to evaluate. Okay, so again, this is just algebra going from here to here. Divide by a number means multiply by its reciprocal, and again, handle the fractional exponents as a root. Okay, Now I'm ready to use the fundamental theorem. I'm going to evaluate at the upper bound. And then I'm going to subtract the value at the lower bound. Okay, luckily for me, these are going to give me whole numbers because 9 and 1 are perfect squares. And when I evaluated that on the calculator, I got a negative 76. Okay, anybody questions about that one? Okay, notice 19 and 20 were definite integrals. Okay, so I get a number out of a definite integral. Okay, it's kind of a cumulative value, or you can think of it as the area under the curve or between the curve and the x-axis, given that areas under the x-axis are negative. Okay, so the areas will net out unless you do something special. All right. This last one, 21, is an indefinite integral. So when I integrate this, I expect not a number, but a function. Okay. So this is a little bit different. Okay. Again, I'm going to rewrite this. Again, I'm writing the x to the third in the denominator as x to the negative 3 because I want to use the power rule on this. Okay. And then repeated power rules give me add 1 to the exponent, write it over the new exponent, pull away the coefficient, add 1 to the exponent, write it over the new exponent. Okay, please remember you're adding 1 to negative 3, so it becomes less negative. Okay. And then there's a plus c for the constant of integration here. I can simplify things a little bit. Okay. Again, if you think about negative 6 divided by negative 2 is a positive 3. Okay, and then this x squared is in the denominator. Okay. Again, more, I think we'll handle it like this. Okay. It doesn't hurt to be able to simplify it a little bit. I think everybody can handle simplifying this. Okay. And again, the advantage of showing your work is, let's say you leave it like this, okay, in more and more marks it wrong, I will give you all the points for it because you did the calculus correctly. Okay. So that's another reason why you should show work. Okay, questions so far? Not seeing any questions. Okay, so far we've only used the power rule for integration. Now let's look at things that are a little bit more complicated. Okay, so a definite integral, the first thing I'm going to do is check. Is this undefined anywhere in this interval? And I'm seeing what looks like a polynomial. Even once this is all multiplied out, it's still a polynomial. So it's not undefined anywhere. Okay, so I'm good. I can actually do the integration. Now let's actually look at what I've got here. Okay, I'm seeing a quantity in parentheses and something that looks like part of its derivative out here, right? If I took the derivative of y squared, I'd get 2y. Well, here's the y. It's just the coefficient that's not right. Okay, what method do you use, okay, when you see this? What method do you use when you see something that looks like a quantity in parentheses and part of its derivative? What method? What should I do? Anybody have suggestions? Yes. Okay, this is where you're going to use substitution. Okay, substitution is the method you use, okay, when you have something in parentheses and a related function. Okay, so you have a quantity in parentheses, okay, and something related, okay, looks like part of a derivative. Okay, so let me call this x, and looks like x prime. Okay. So when they're related, you use substitution. If they're not related at all, that's when you use by parts. Okay. Sometimes by parts will work on a substitution problem, but it's unnecessarily complicated. Okay. So try to recognize these two cases. All right. So I'm going to, again, always let u be the thing in parentheses. Okay. Don't pull in the derivative. Okay. That's part of the point. Let u be the thing in parentheses. Or if you've got an exponential function and you've got a function in the exponent, let u be that. Okay. Provided you have part of the derivative of that exponent somewhere else in the integral. Okay. So I'm letting u be y plus 1. Then the derivative of u with respect to x is 2y. Now, this is a place where a lot of people struggled on exam 4, folks. Okay, so please make sure you understand this bit. What I am trying to do is I'm trying to match what's in my integral right here. Okay, I've already got the y squared plus 1 taken care of. That's going to be u. Now I need to match the rest of the derivative, and I'm seeing y dy. Okay, so, well, I want to get dy over there, and I'm sorry I wrote dx, it's dy. All right, so I'm going to multiply both sides by dy. That gets rid of it over here, and I get du equals 2y dy. Well, I'm close, except I've got this 2 that's in the way. All right, so I have to get rid of the 2, all right, by dividing both sides by 2. All right, and now I have a y dy on this side, which is what I want. I need to get it to match what's in the integral. Now, instead of putting in du over 2, I'm writing 1/2 du. Why is that? Dividing by a number is the same as multiplying by its reciprocal. Okay, if I divide something in half, that's the same as taking half of it, right? So everybody all right with that? Okay, so then the integral, the substitution becomes this. Okay, I'm going from 0 to 1. Again, I'm not going to put the bounds on here because, again, a lot of folks say, well, why didn't you change the bounds to u bounds? We can do that. And I noticed from exam 4 that Moore wants you to leave u in. It doesn't want you to substitute it back. Okay, you can do it either way. All right, and I guarantee you most of you got the correct answer on the definite integrals. Let me show it to you with substituting for u bounds, okay? Here's the upper bound. Okay, I'm going to take my 1 and I'm going to put it in and square it. Okay, 1 squared is 1. Okay, so this upper bound would be 2. Okay, and let's try it with the lower bound. Okay, 0 squared plus 1, then my lower bound becomes a 1. Now, because I converted my bounds to u bounds, I do not need to put y back in there. Okay, I can just evaluate the definite integral with these u bounds. That's kind of the way the problems in the tests are set up. I know I told you you can do it either way, and I know that confused some of you. I gave you the credit on exam 4. Okay, so kind of, again, pay attention to what the question's asking you. If it's asking you for the u, what are the u bounds, what's the new upper and lower bounds, they want you to convert. Okay, so I'll show you how to do this. Okay, so again, what have I got? Okay, my y squared plus 1 to the 5th is now u to the 5th. Okay, and the y dy is 1/2 du. Okay, that's the substitute piece. Okay, I'm going to pull the 1/2 through. Okay, so now I have the integral from 1 to 2 of u to the 5th du. That's easy. Bring down the 1/2. Don't lose whatever you pull through the integral sign. This is going to be u to the 6th over 6, evaluated from 1 to 2. And again, I'm not putting the y back in because I changed the bounds. Okay? If you don't change the bounds, then you've got to put the y back in. Okay? All righty, so doing that, okay, gives me, where am I? Okay, so I have to basically put in my upper bound, which is 2. First of all, this is going to be over 12, right? So this is 2 to the 6th over 12. Oh, no, I don't need the 12 because I factored that out. Okay, here's what you can do. Okay, since you've only got one term here, you can pull this 6 out here and you can make this a 1/12. And then all you're evaluating would be your upper bound would be u to the 6th. Okay, so what did I do here? I pulled out a 1/6 and I multiplied the 1/2. I'm doing that because I've only got one term here. So I've got 2 to the 6th minus 2 to the 1, u to the 6th, rather. I'm sorry, having a problem with my tablet. So 2 to the 6th minus 1 to the 6th. Okay, so here's upper, here's lower. Okay, so you just take a calculator, and 2 to the 6th, I believe, is 64. So this is going to be 64 minus 1 is 63/12. And I'm pretty sure I can divide a 3 out of both of those. Okay, everybody all right with this? Putting the y back in makes for more complicated evaluating. Okay, but if you're going to keep u in, then remember to change the bounds. Okay, everybody all right with that one? Okay. Not seeing questions on 22. Let's look at 23. Okay. Let's take a look at 23. Okay, the first thing I'm going to do is check, is this function defined everywhere in this interval? Okay, so look at 23. Is the function defined in the interval of integration? I'm asking you a question. Is the function defined in the interval of integration? What do you think? The interval of integration is from 1 to 5. Is this function undefined anywhere in there? Okay. Yeah, it's undefined when t is 4. Okay, and this factor is still going to wind up in the denominator of your integral. If you were to do an indefinite integral here, you'd still wind up with this undefined piece, okay, in the denominator. So basically, your fundamental theorem doesn't apply. Okay, you may have noticed, and so basically you can't do it. Okay, you can't do a definite integral on this over that, over these bounds. Okay, if they move the bounds from 5 to 6, you could do it. Okay, or if it was from -1 to 0, you could do it. The problem is that 4 is in here. Okay, now if you remember from exam 4, the type of problem they show you for this, they don't necessarily show you one and ask you to do it. They show you somebody's work and they ask you, find the error. Is this correct? And the student will have gone ahead, done the integral, will have plugged in the values and gotten a number. Okay, and they'll ask you, is that correct? Check that the function is not undefined anywhere in here. If it is, then the answer is no, it's not correct. And the reason is the function's undefined at this point in the denominator. So the fundamental theorem can't be used. Okay, a lot of folks had trouble with this question on exam 4. Okay. If you had a way to do a definite integral, like say with a TI-84, it would have given you an error if you actually tried to integrate over those bounds. Okay, but I realize not everybody's got a TI-84. So I was generous when I graded it, okay? But I'm telling you now, watch out for those types of problems, okay? Here's an exponential, okay? Again, I see a function up in the exponent, so I'm going to use substitution. The derivative of that exponent would just be a 6, okay? So the power on x is 0, okay? And I'm not seeing any x's, so we're good. Substitution will work. So let u equal the exponent. Okay, so du equals 6 dx. I don't need the 6, so let's divide it out. All right, and then I have this. All right, pull it through. You might remember that e to the u is its own, or e to the x is its own derivative, its own integral. Okay, so all right. Some of you might have even remembered something that says, well, if I have an exponential and I'm integrating it, I just divide by the derivative of its exponent, and you could get here all in one step. Okay, but here it is in steps. Okay. Again, here's a definite integral. All right, and I want to check to see if any numbers in this interval here that I'm integrating over will make this 0. Okay, what you want to notice is you've got a plus sign here. Okay, so the only way the denominator could be 0 would be as if this first quantity could ever be negative, right? It'd have to be equal to -1. And look at the square. No matter what you plug in for x, you're going to get a positive number when you square it. So there's no way 3x squared can ever be negative for any value of x. Okay, so that's a quick way to tell, hey, this is not going to be a problem. It's never going to be 0 anywhere in this interval. Is everybody okay with that check? Okay. All right, now I have to decide how to integrate. I'm noticing a quantity in the denominator. I can rewrite this integral like this. Okay, I could take quantity out like that. Okay, if you want. All right, and now what you want to notice is if you took the derivative of 3x squared, what would you get? You'd get 6x. Okay, So I'm seeing a 3x out here. So the power on x is correct to be the derivative. Just the coefficient is wrong. We can fix that. What you want to see here is something in parentheses times what looks like part of its derivative. So we're going to use substitution. Okay, and you're going to let u be the thing that was in parentheses, which is 3x squared plus 1. Then du dx is 6x. Again, I'm trying to match this stuff that's in the integral, okay? So the first thing I'm going to do is multiply both sides by dx. That's going to give me du equals 6x dx. And the last thing I need to do is I need to turn that 6 into a 3. Well, I can do that by dividing it in half. Okay, and that's going to give me 1/2 du equals 3x dx. All right, and now you can see I match. Everybody okay with that one? All right, the substitution is now going to be from, I can put in my u bounds if you want. I can say upper equals 3 times 4 squared plus 1. Okay, so 4 squared is 16. 3 times that is 48 plus 1 is 49. And my lower bounds is 3 times 0 squared plus 1, that's 1. Okay, so my u bounds are 1 and 49. Okay, and then now I don't have to put my x's back in there. All right, so substituting in, I'm going to get 1 over u, or u to the minus 1. Okay, I'll stick with the minus 1 since that's what I'm using. U to the minus 1. That's the first part. And then I have the 3x dx is 1/2 du. Okay. All right, I'm going to pull the 1/2 through the integral. And now I'm integrating u to the minus 1 du. Well, you should remember from your integration summary, which is in the course notes, right? It's, if you can find it, it's one of the first sections on integration. So this integrates as ln. So I have 1/2 ln u evaluated from 149. Okay, so that gives me 1/2 ln 49 minus ln 1. Okay, again, ln 49 is asking you, what do you have to raise e2 to get 49? Beats me. Okay, so I'm going to leave that. What do I have to raise e2 to get 1? That's 0. So this is 0. So my answer is 1/2 ln 49. And you can approximate this on your calculator if they want an approximate value. Okay, if you can get here, okay, in your work, that's full points as far as I'm concerned. Okay. All righty. Number 26. If you look at number 26, okay, I am seeing two functions. One of them's exponential and one of them's algebraic. Okay. Part of the derivative of this would not have an x in it, right? Because this power is already 1. So if I did take the derivative of 4x, I get just 4. So this isn't the derivative of that. Likewise, an exponential isn't the derivative of a linear. So these are unrelated functions. That means I get to use integration by parts. Okay, and again, in 26, which function should be u? Anybody remember how to choose which function should be u? The rule says if you've got a log, pick the log as u. If you don't have a log, which function should be u? Anybody remember? Okay. I'll write it in the chat. Pick a log if there is one. Otherwise, pick the algebraic to be u. Okay, so here's the rule. Pick a log if there is one. I don't have a log. I do have an algebraic function. I have 4x. So I'm going to let 4x be u equal u. That means e to the 4x is dv. Remember, you've got u and dv here. Okay, so we're going to differentiate u, and we're going to integrate dv. Okay, that's how we do this. All right, so here's the u. If I differentiate it once, I get 4. If I differentiate it again, I get 0. 0 is what stops the process. Okay, if you have a log function, it will never become 0 when you differentiate it. So you differentiate it once and you stop. Okay, and then again, you're going to have to pull out the last row of your table as an integral. But because it's probably going to have a 1 over x in it, it's going to make the integral simpler. Okay, so remember the rules for integrating by parts. If I've got an algebraic function as u, like I do here, I'm just going to stop when it becomes 0. Now let's integrate dv. Okay, and again, you might remember from this one up here, okay, I'm just going to keep dividing by the derivative of the exponent. So this is going to give me e to the 4x over 4, e to the 4x over 4 times 4. Okay, so again, this is a simpler one to integrate. Just keep dividing it by the derivative of its exponents, and they're going to queue up in the denominator and they're going to multiply each other. Then you do your diagonal arrows. This one's plus, this one's minus, and you pull these out of the integral as products. So I have 4x times e to the 4x over 4. That's my first product, and it's positive. My second product is negative. Okay. It was an indefinite integral, so I have a plus c. And then the rest is just cleanup. I'm going to divide out the 4's here. And I'm going to divide a 4 out of the numerator and denominator. Okay, anybody problem with integration by parts? Okay. We're finally to the applied problems, and I can tell you right now, we can't get to all of them in the time we have left, but let me pick and choose, okay? I can kind of show you how to set them up here and entertain any questions you have. When I send you the work, I'll show you everything worked out. Okay, when I upload the work, it'll all be worked out. Okay, with this one, you have an improper integral. Okay, so this is the one where you need to take a limit as c approaches infinity and then put c as your upper bound. Okay, and again, what do you need to remember about this? This is easy to integrate, but what you want to remember is if you have a fraction and the denominator is getting very large, the fraction approaches 0. I noticed a lot of you were able to integrate it properly, but then you weren't able to determine what the limit was. Okay, if I take a limit of something over x cubed as x cubed gets really large, this is going to be 0. Okay, so again, don't worry too much about this. I would guarantee you that this function is actually has an actual value, okay, once you do the integration. Okay, so this one is asking you to geometrically determine the area, okay, under the curve. Okay, so basically find the area here. Okay, now you have to realize you've got a negative area down here. I guess I should use a highlighter rather than a blob like this. This is negative down here. Okay, and then it's positive up here. So all you need to do is find the area of those figures. You may or may not realize that these two figures are both trapezoids. Okay, and the formula for the area of a trapezoid is 1/2 its height times the sum of its bases. Okay, so geometrically, you can find the area by just looking at the size of things. Okay, this is 4, this is 2, and the height is, oh no, I'm sorry, it's scaled so that they're double. Okay, so this is 2, this is 1, and the height is 2. Okay, but I'm using a -2 because I'm below the x-axis. Okay, so this first blue trapezoid would be 1/2 of -2 times 2 plus 1. So that's -1 times 3. That area is -3. Again, negative because it's below the x-axis. They're just asking me to evaluate the integral. Okay, and when you evaluate an integral like this, the negative and positive areas net out. Okay, let's try the red trapezoid. Okay, here, this is going to be 2 across. It goes from, this is from 5. Okay, so this is going from 3 to 5, so that's 2. This is going from 2 to 5, so that's 3, and it's 2 high. Okay, so this is 1/2 times 2. Okay, so that's 1 times 5 is 5. Okay, so net area is -3 plus 5. The value of the integral is 2. Okay, so that's how you do that one. Okay, this problem was actually on exam 4. Okay, and if you're finding the area between curves, again, this is one I won't do. I'll just show you the setup. You kind of want to graph this. All right, so this is, here's a 20 down here. Here's a -12. Okay, so you're going to graph the two curves. The first one's going to look like this. Okay, that's the first curve. And the second curve is going to look like this. Right? And you want the area in between. Okay, so in order to do that, you've got to find the points where they intersect. I'd recommend you do this with Desmos. Okay, I know I did it with Desmos, and I found these are 4, 4, and this was -4, 4. Okay, so to do the integration, the bounds on the integration go from the intersection points. And in this case, the top function is always on top. And this function's always on bottom. That's how you set it up. Okay, and then basically you do some algebra here. Okay, you'd be able to combine the terms in x squared and combine the constants, then integrate and evaluate. Okay, the only hard thing about this problem is doing the graphing and determining the bounds on the integration. Okay, so before I go off this page, let me ask any questions so far. Any questions so far? Okay. All right. Okay, we have 4 applied problems left. Okay, one of them is basically building an exponential function from data in a problem. Okay, that's a college algebra problem. It's not even really a calculus problem. So I'm going to skip that one. That's number 30. I will work it out for you. Okay. 31 is essentially asking you to maximize profit. I think I will show you that one. Okay. 32 is a lot similar to problems that we've done in the past, where you've got seating in an arena, and for every dollar you raise the price, the attendance drops off by so many thousand, and they want you to figure out what ticket price will maximize sales. I can show you the setup for that, but I'm not going to work it through. The last one is an implicit differentiation one, and I'd like to show you that. So hopefully you can hang around for another 10 minutes or so while we go through these. Okay, so 30 is the one that's just an exponential model, no calculus. So I'm going to skip that for now. Okay, I'll show it to you when I upload my work. Okay. This one I'm going to try to work through. Okay, I have a cost function for the production of X pair of a certain type of sunglasses. If they're sold at a price of $38.50, find the number of pairs which should be sold to maximize profit. What you want to notice here is you don't have a profit function. You need to build the profit function. Okay, and the profit function is revenue minus cost. You've got cost function, so you need a revenue function. Now they tell you the price of the sunglasses, right? Okay, so your revenue is just your price times the quantity you sell. Okay, you've got to remember that much. Okay, so revenue is price times the quantity you sell. Now I can build my profit function. I have 3850x minus all of the terms in the cost function. Okay. Again, I'm not going to work through the algebra step by step, but I'll just show you once you combine like terms here, you're going to distribute your minus sign to all these terms. Combine like terms, you're going to get 37x minus 640 plus 0.50x. Okay. Then all you have to do to figure out what you've got here is differentiate your profit function. First term gives you a 37. The middle term's a constant, you get nothing. 2 times 0.5 is 1. Okay, so this, and drop the exponent by 1. So the last term here, when you differentiate it, gives you x. Set your derivative to 0. Okay, and you get x equals 37. Okay, you can check it's a max by the second derivative test. P double prime of x equals -1. Concave down everywhere. Okay, this proves it's a maximum. Okay, so they didn't ask you for what maximum profit was, but you know that if you sell 37 pair, you're going to earn a maximum profit. And again, if you wanted to find the maximum profit, you would plug your 37 in here for X to get your maximum profit. Is everybody okay with 31? Everybody okay with 31? Okay. All right. Let's look at this one with the arena just to show you how to set it up. They play in a hockey team plays in an arena with a certain capacity. When the ticket price is $12, average attendance was 11,000 people. A market survey indicates that for every dollar you lower the price, attendance increases by 1,000. How should the owner set ticket price to maximize revenue? Well, you need a revenue function, and that's basically price times amount sold, right? Price times quantity. Well, to maximize your revenue, they're saying take your $12 price and lower it by some amount. Okay, let's call that number X. This is the amount we're going to lower it by. Okay, let's say it's $1, right? So for every dollar you do that, what happens to the amount you sell? Well, you've got 11,000, and they say it increases by 1,000 for every dollar you drop the price. Okay, so here's the way you set these up. Okay, you've got price minus the difference, okay, how much you're going to drop it by, and then you have attendance plus whatever factor they give you times that X. Okay, then what you're going to do with this is you're going to FOIL it out. Okay, then you're going to take its derivative, okay, and figure out what X needs to be. Now just remember, X isn't the price, it's the change in price. Okay, it's the amount you're going to subtract from the price to get your optimal revenue. Okay, everybody okay with setup on 32? Again, I'll work it out for you in the notes, but I want to make sure you understand how to set it up. Anybody questions about the setup on 32? Okay, let's take a look at 33. This is an implicit differentiation problem. We have a volume of a cube, okay, and the volume of the cube is increasing at the rate of 10 cubic centimeters per minute. Okay, how fast is the surface area increasing when an edge is 30 centimeters? Let's call each edge of this cube S. Okay, and we know they're all 30 at the instant we're interested in. Okay, they give you dV dt, and they say that's 10. Okay, you want to answer questions about surface area. So the surface area of a cube, I'm going to just call it A to keep things simple. Okay, think about this. It's got 6 sides. Each side is an S. Okay, so the surface area of one of the sides is S squared. Okay, S times S, and there are 6 of them. So there's a formula for the surface area of this cube. Now, if you were to differentiate this implicitly with respect to time, okay, you can see you get a dA dt, right? Then you get 6 times 2s ds dt, right? That's an implicit differentiation of surface area. Well, dA dt is what I want. I know at this instant S is 30. I got that. I'm missing this. I'm missing how fast the sides are changing when the sides are 30. So how do I do that? Well, what I need to do is I need to do the volume. Okay, and the volume is side times side times side. Okay, and I need to differentiate it just to get ds dt. I'm differentiating implicitly here. dV dt equals 3s squared ds dt. Okay, so I'm implicitly differentiating my volume formula. Okay, and I'm doing it not to get dV dt. They gave me that. I want to solve for ds dt. Okay, so I'm going to plug in what I know. dv dt is 10. S is 30. And see if I can solve for ds dt. Okay, so that's 10. 30 squared is 900, and 3 times 900 is 2,700. Okay, so all I have to do is divide both sides by 2,700. Okay, I can divide a 10 out of each of these. Okay, so I've got my ds dt. Now all I have to do is go back to my implicit derivative for surface area. You can see 6 times 2 is 12. Put in my 30. And now I can put in my 1 over 270 and work all of that out. That's just a calculator problem. Okay, the 270s in the denominator, the 12 times 30, okay, which is 480, is up in the numerator. When you simplify that all out, you get the area is changing at a rate of 4/3. Now it's an area, so centimeters squared per minute. Okay, that's our rate. Okay, I kind of think problem 33 is the trickiest one here because it requires you to realize you've got something missing and then go back and figure it out. Okay, so questions on number 33. How we doing? Anybody questions on this last weird one? Okay, so what this means is as your volume increases by 10 cubic centimeters a minute, the surface area is also increasing by like 1 1/3 square centimeters a minute. Okay, maybe this is a cube that's being slowly inflated or something like that. Okay, I'm going to be coming back. So I'm going to stop sharing. Okay, and coming back to the meeting, I'm going to ask you any questions on anything. Okay, I see a question from Olivier. Any password